So we will wait for 10 more minutes and then we will start the session. Okay, so we'll start the session now. So, hello everyone, and welcome to this NPTEL TA session for the Fluid Flow Operation course. And this is week 5 for the TA session. And myself, Amaan Dash, and I'm a PMRF research scholar from IIT Kharagpur. And in this TA session, we will be solving some numericals from the course content of week 5, and that may be helpful for you for solving different questions from the assignments and also from the examinations. Okay, you can expect similar question from your exam and also similar question in the assignments. Okay, so let's start. So these are the session links. So first one will be the usual link that we will be using, and the second link is in case the first link does not work, we will be coming back to the second link, okay, in case of any problem. But the first link is the main link that we will be using for our sessions. Okay, so let us start with the first question, and let's see. An ideal fluid is defined as the fluid which, and the options are, is compressible, is incompressible, is incompressible and non-viscous, and has a negligible surface tension. So which of these options will be correct? So this is pretty simple. So an ideal fluid by definition should be incompressible and it should be non-viscous. Okay, so it should be incompressible and non-viscous. So this should be the correct option. Okay. Now let's go to the next question. The fluid forces considered in the Navier-Stokes equations are which of these? Pressure, viscous, turbulent, body, pressure, viscous, body, pressure and turbulent, body, viscous and turbulent. So which of these options or which of these forces are considered in the Navier-Stokes equation? So, if you see the right side of the equation, the right side of the Navier-Stokes equation, you will see the terms like dou p by say dou x, say let x component we are considering, plus we will be having mu into all the terms, plus we will be having some rho into say gx. So the first term is the force term related to pressure. This is the term related to the viscous forces, and this is nothing but the body force. So the forces which are considered in the Navier-Stokes equation are, one will be the pressure force, one will be the viscous forces and the body forces. So we have the body forces, pressure and viscous forces. So this should be the correct option. Okay, I think this is pretty much clear now. Now let's go to the next question. The Navier-Stokes equation describes the motion of what? And the options are solid substance, non-viscous fluid, viscous fluid, or a gas. So this is pretty much simple. We know that the Navier-Stokes equation describes the motion of a viscous fluid. Okay, so the answer will be viscous fluid. Okay, so let's go to the next question. In the Navier-Stokes equation, the convective acceleration in the inertial term is a linear relation, non-linear relation, or is the term negligible, or none of the above? So which of these things, which of these options do you think is correct? Okay, so it's a non-linear term. How? Because if you see the convective acceleration term of the Navier-Stokes equation, that is the left side of the Navier-Stokes equation. So the equation is something like this: rho into, so we have dou u by dou t plus u dot del right. So if we expand this, say for a particular component, say for example the x component of velocity, say u, so we will be having rho into dou u by dou t plus u into dou u by dou x plus v into dou u by dou y plus w into dou u by dou z. So you can clearly see that there is a product of u and gradient of this velocity in a particular direction. So clearly this is a non-linear term. Okay, so since these terms all are non-linear terms. So we can see that the convective acceleration in the inertial term of the Navier-Stokes equation is nothing but a non-linear term. So this term is a non-linear term. Okay, so the answer will be non-linear. Okay, so I think this is pretty much clear, and now let's go to the next question. A low value of Reynolds number means that dash are large in comparison with dash. So the options are these. Okay, so we know that Reynolds number is equal to rho v, say d by mu. Okay, so that is nothing but we can say is the ratio of inertial forces by viscous forces. Okay, so it is given that for a low value of Reynolds number, that means if the Reynolds number is low, that means clearly the viscous forces will be dominating or will be larger in comparison to the inertial forces. So we will be having, if it is a low value of Reynolds number, that means the viscous forces are large in comparison with the inertial forces. Okay, so we will be having viscous forces and inertial forces. So this should be the correct answer. Okay, okay, so now let's go to the next question. Consider a fluid is flowing between two stationary parallel plates, and the velocity near the plate will be what? So we have two parallel plates, okay, stationary parallel plates, and the velocity near the plate, any of this plate, the velocity of the fluid near any of this plate will be equal to what? And the options are 0, maximum, minimum but not 0, or none of the above. So let's see the solution. So the velocity will be 0. Why? Because we know from the no slip boundary condition, the velocity of the fluid near the wall will be equal to the velocity of the stationary wall. Okay. Now that means here velocity of the fluid should be equal to the velocity of the wall. Now it is given that this is a stationary parallel plate. That means the velocity of the wall is equal to 0. Okay. So the velocity near the plate, that is u, will which is equal to u wall, will also be equal to 0. So the velocity near the plate will be equal to 0. Okay. Okay, so now let's move on to the next question. Consider the balance of forces acting on the respective faces of an assumed small volume dx dy of unit width in a fluid as shown in figure. So you can see the figure, and this is a unit width. That means if we extend it, it's a unit width, and we have a small volume which has dimension dx and dy. Now the equation for the velocity distribution is given by this. So this is the region where the fluid is flowing, and there is a balance of forces, and we got a velocity profile of this, which is a parabolic equation. To obtain the maximum velocity, that is u max, y can be replaced by h by 2, and du by dy will be 0. Based on the details, find out the mean velocity. So what will be the mean velocity, and what should be its relation with u max? So these are the options, that is whether u mean is equal to u max, or u mean is equal to 0.5 u max, u mean is equal to 0.67 u max, or u mean equal to 1.5 times of u max. So which of these options will be correct? So here it is given that there is a balance of forces. That means there are pressure forces and we have shear forces. So these forces are balancing each other, and then we are getting a velocity profile, which is given using this equation. So how is u max related to the u mean? Okay, let's see. So here it is given that there is a balance of force acting on the respective faces of the assumed small volume dx dy of unit width, and the velocity distribution is given as this, which is a parabolic equation. To obtain the maximum, y can be replaced as h by 2. So we know how to obtain the maximum velocity, and at what y we will be getting that maximum velocity. So to get that, we have to, what we have to do is dou u by dou y should be equal to 0. Okay, that is du by dy will be 0. So if we differentiate the u with respect to y, let us say this term, let us say this term to be a, that is some value, some constant value of a. Okay, so if we differentiate u with respect to y, we will be having a term into, we have h into y, so if we differentiate with respect to y, it will be h minus, here we will be having y square, y, if we take y inside, we will be having y square, and if we differentiate it with respect to y, we will be having 2 times of y, and this should be equal to 0. Okay, so this term a is not equal to 0, because if this term a is equal to 0, then u will always be equal to 0, which is not feasible, and in such a case this u, there will be no such velocity profile only. Okay, this u will always be equal to 0, so a is a non-zero term. So this should be equal to 0, h minus 2y should be equal to 0, that means y should be equal to h by 2, right? So to get the maximum, that is du by dy, we can get the maximum at y is equal to h by 2. So if we substitute y, this y, back into this equation, what we will be having is that u, let's say max, say u m is equal to this term a into, we will be having h minus y, we have h minus this y will be equal to h by 2, correct? And here we have another y, so that will be equal to h by 2. So if we just simplify this, h minus h by 2 is equal to h by 2 into h by 2, so we have a into h square by 4. Okay, so we got that u max is equal to a into h square by 4, right? But now we have to find out how u mean, that is the mean velocity, is related to this u max. So for that, first we have to find out what is this u mean. So we know that if this is the width, some width, and from here we are having some flow, right? And from this direction we are having some flow. So the mean velocity, or the area mean velocity, how we can calculate? We can calculate using integration, whatever the velocity we are having, times of dA by integration of dA, correct? But here we have a, this area A is nothing but a rectangular geometry, that is this height and some width, and along this height we have a change in velocity, that means u is a function of y, and we have a unit width, that means this width is equal to say 1. Okay, so this term, this a, will be replaced by what? This area is equal to what? Sum this y into h, into w, and this w term is equal to what? Is equal to 1. So what we are left out with is integration of u into dy by integration of dy. Correct? Because this area is a rectangular area, so it will be y into w. Here also it will be y into w, where w is given to be unit width, so w is equal to 1. So the integration is left out to be u into dy. Here also integration of dy. And this dy, this y, if you can see the coordinate system is here, so the y will be changing from this point to this point, that is from 0 to h. Okay, so the integration of y will be changing from 0 to h, and here also 0 to h. That means that is equal to, this will be nothing but it will be equal to h. So we have 1 by h into integration of 0 to h u into dy. Correct? So we have to find this mean velocity by substituting the value of u from here into this equation. That means here we have 1 by h into integration of 0 to h, and this we can write it as a into h minus y into y into dy. Right? Correct? That means that is equal to, if we write 1 by h, or we can take a as common. So here we will be having a into y. So if we integrate it, it will be a into y square by 2. So here we will be having h into y square by 2 minus, here we are having y square. So if we integrate it, it will be y cube by 3, and this has a limit from 0 to h. Right? So if we substitute the value, if we put the limits here, what we will be getting? We will be having a by h. Here it will be h square, so it will be h cube, and here also it will be h cube. So if we take h cube to be common, we are having 1 by 2 minus 1 by 3. Right? So if we just cancel one of the h here, so we will be having a into h square by 6. Right? So what we got is that this is u mean. So 1 minute. So this is u mean, this what we are getting as u mean, and this we have u max. This term we are having as u max, and we have to find the relation between them. Okay, so that is pretty much simple now. So here we have ah square, here also we have ah square, so obviously ah square, what we have is nothing but we can write it as 6 times of u mean. We have ah square by 6 is equal to u mean. So this what we are getting, the value of ah square. Just substitute in here, what we will be getting is that um is equal to, we have ah square which is equal to 6 times of u mean, so we have 6 times of u mean by 4. Okay, 6 times of u mean by 4, which is nothing but if we cancel it, it will be 3 and it will be 2. So this implies what we have is u mean is equal to 2 by 3 times of u max. Okay, which is also equal to, if we write 0.66 or 0.67 times of u max. Sorry. So u mean is equal to 0.67 times of u max. Can write 0 u mean is equal to 0.67 times of u max. So this is the relation. I hope this is clear, right? So how we are getting this relation of u mean, the average velocity, and how it is related to the maximum velocity. Okay. So I hope you understood this question, how it is coming, how the mean velocity in this case where the velocity profile is given, and how it is related to the maximum velocity. Okay, so now let's go to the next question. For the laminar flow of a fluid in a circular pipe of radius r, the Huygens-Poiseuille equation predicts the volumetric flow rate to be proportional to what? Radius, radius square, radius cube, or radius to the power of 4. So from Huygens-Poiseuille equation, we know that delta P is equal to 32 mu L V by D square. So if all these terms are like pressure drop, viscosity of the fluid, length of the pipe, and diameter, all these are constant terms. So what we will be getting is that velocity is proportional to d square. Correct? But for here we are asking what is the volumetric flow rate. So for volumetric flow rate, we know that Q is equal to area into velocity. So now this is a circular pipe of a radius r. So the area is proportional to r square. and the velocity is proportional to d square, which is also proportional to r square. So we have velocity proportional to r square. So finally what we are getting is that the flow rate, volumetric flow rate, what we will be having is proportional to r to the power of 4. Okay, so from this Huygens-Poiseuille equation, the volumetric flow rate, that is the Q term, will be proportional to r to the power of 4. Okay, so this is the correct option. Now let's go to the next question. In turbulent flow, the average velocity is dash of the maximum velocity. And the options are equal to 0.5, less than 0.5, more than 0.5 and up to 0.85, or greater than 0.85. So yes, it will be in the range of 0.5 to 0.85. Okay, you can directly get it from the lecture slides also, how, why we are getting such a relation. And for laminar flow, obviously again it will be different. Okay, okay, let's go to the next question. The turbulent eddy viscosity varies with what? Pressure, temperature, pH of the fluid, or flow conditions. See, for laminar flow it will be zero point 0.5, but if we have different geometries we will be having different relations, okay? So it all depends on the geometry what we will be having. But in turbulent conditions, since the flow itself is not fixed, the flow is changing every time, so it have a range like zero point 0.5 to 0.85. But if we are using a laminar flow, it will be having, for a given geometry it will be fixed, okay? So yes, here the answer will be flow conditions, okay? The eddy viscosity varies with flow conditions. Let's go to the next question. The mixing length depends on the what? Velocity gradient, distance from the wall, both A and B, or none of the above. So yes, the mixing length depends on both these factors, velocity gradient and the distance from the wall. Now what is mixing length and how it is, why it is depending upon all these things, you can read it from the lecture slides itself. It is clearly explained in the lectures, okay? How it is coming. What is this mixing length and what will happen if the distance is less, or what if the distance will be higher or the velocity gradient will be high, how this mixing length is affected, you can see in the lectures notes directly or the lecture videos, okay? So the answer will be both A and B. Okay, so let's go to the next question. The Reynolds number will be maximum in case of which one? Okay, so we have three velocity profile A, B and C, and we can see here. So in the three cases, which case the velocity or the Reynolds number will be maximum? And the options are whether it is the velocity, whether it is the profile A or profile B or profile C or none of the above. Okay, so let's see the answer. So it is option C. Now option C, this velocity profile should have the maximum Reynolds number. Now why it should be, like why this option C should have the highest Reynolds number or maximum Reynolds number? So let's see. Suppose we have two layers or two, some say for example pipe or two parallel plates or whatever, and there is a flow. Okay, now when the Reynolds number is low, we know that the flow will be, or the layers of the fluid will be or parallel to each other, right? So consider that to be a, say, laminar. We are having some kind of a laminar flow. So when we are having this laminar flow, what will happen is that, say, this layer will be having the layer that will be close to this wall will be having a zero velocity because of the no slip boundary condition, and at the center we will be having the velocity which will be the maximum, right? We will be having the maximum velocity. So we will be having a lot of change in the velocity. So if here the velocity is 0, here we will be having a high velocity, right? So we will be having a profile like this. That means there will be a lot of change in the velocity from u to u max, very much change in the velocity. But what happens when the Reynolds number is increased? Okay, so initially we have layers that are all parallel to each other, okay, because of this laminar flow. Now say we have a higher Reynolds number, or moving to some high Reynolds number, or just going and going, and then we move to the turbulent region, right? So Reynolds number we have increased and we have moved to a turbulent region. Now what will happen? That means, say for example, if it is creating some eddies, okay, or some disturbance it is creating. So what will happen? Suppose we have a eddy that is created here. That means suppose some disturbance that is created here and it was having some u max. That means some maximum velocity. So what will this eddy try to do? Say this layer has a velocity that will be less than this layer, because this is the maximum layer and here we have the zero velocity. So this velocity will be somewhat less than this u max. This eddy or this circulating region, what it will try to do, it will try to make this u balance with this u max. That means suppose say we have u max here and this will be u, and they are mixed up. Suppose we have the velocity u1 and we have a velocity u2. Some fluid we are there are two fluids that are moving and we are mixing this fluid. So what will happen? They will try to balance each other and will have some average velocity that will be in between u1 and u2. Say this is say 10 meter per second, this is say 5 meter per second. So when you mix them while flowing, they will try to attain a velocity which will be in between them, right? That means these circulating regions, what they will do is try to balance out or to average out this velocity. And this is not, this eddy is not only in the central region, but it will be created here in towards the center in various different regions like here and here. So what they will try to do is that they will all try to average out this velocity. Okay, that means instead of this u max to u0, they will try to have a balance, or they will try to balance this velocity. That means instead of having this much large difference in velocity, due to this balancing effect, we will be having a rather flat velocity. Okay, that means here you can see that from here to here we have a high change in velocity because all the layers are parallel to each other. But here, because of this mixing effect, what we'll be having is that this velocity are almost similar. Okay, because we will be having this some kind of mixing effect. Okay, so because of this we will be having a almost flat velocity profile as we move to a higher Reynolds number. Okay, Like if we move further higher, and this will happen if we go on increasing the Reynolds number. That means the velocity profile try to be more flatter. Okay. So from this concept you can see that this is a low Reynolds number flow, and this is a in between Reynolds number flow, and then again the Reynolds number is increased, so we have a high Reynolds number flow, because this is a very much flatter velocity profile as compared to other two options. Okay. So now you could able to understand why this is option C, why option C will be the highest Reynolds number or the maximum Reynolds number in this case. I hope this is pretty much clear that why this effect of flat velocity profile is coming for a high Reynolds number and a rather very much steep velocity profile in case of a low Reynolds number flow. Okay, I hope this is clear. This concept is clear. Okay, so now let's move on to the next question. For a 2D flow, the instantaneous velocity of fluid particles in the turbulent flow condition is expressed as u is equal to u bar plus u dash. Here u dash represents what? And the options are average mean velocity, the maximum velocity, overshoot velocity, or the fluctuating velocity. Okay, say we have a velocity profile and it is some random velocity distribution. Okay, so in such a case, say we have a turbulent flow and the velocity has some random distribution with respect to time. Okay, so in such a case, what we generally do is that we define a mean velocity. That means we have a mean component of this velocity, say this value, which is the u mean, and then we have another term which represent the deviation from this mean value. Okay, so the velocity is equal to sum of these two conditions. That means this is the deviation, that is this is the u dash, and this u dash is called the fluctuating component. That means how far is the velocity from this mean condition, how it is fluctuating from the mean condition. So this component is called the fluctuating component of the velocity. Okay. So this is the fluctuating velocity or the u dash component of the velocity. Okay, so now let's go to the next question. The thickness of a boundary layer dash with the distance x from the leading edge and dash with increasing free surface velocity. And the options are so which of these options do you think will be the correct one? Okay, so let's see. Suppose we have a some kind of a flat plate. So when we are having a flow, so a boundary layer will be created, and as we move along in the, say for example, this is the x direction and it is starting from here. So as we move along this plate, we know that the boundary layer will be growing, correct? So the thickness of a boundary layer increases with the distance x from the leading edge. So if, say for example, this is the leading edge and we are having some distance x, so with increasing x we will be having a more thicker boundary layer. So this is the boundary layer thickness delta. Okay, so the thickness of the boundary layer will increase with the distance x from the leading edge. So this will be increase, and it dash with increasing free surface velocity. Now say for example we have some kind of a velocity and this is the boundary layer. Now if we increase this velocity, this u velocity, what will happen? It will try to suppress this boundary layer. Like as the flow velocity increases, this boundary layer will be suppressed and will be more closer to the wall. Okay, so this is a low velocity and this is a higher velocity, say u1 and u2. Okay, so this will be more closer to the surface. So what will happen with increasing free surface velocity? The boundary layer thickness will be decreasing at a particular location. The boundary layer thickness will be decreasing if we increase the free surface velocity. So the option will be it increases, and then the second one will be decreases. Okay, so is this clear? Okay, so it increases and option B decreases. Okay, okay, let's go to the next question. The local drag coefficient is proportional to what? So this is, I think, a direct relation. If you know the relation, you can directly say the answer. So yes, option D. Okay, so yes, it is Reynolds number to the power of minus zero point 0.5. So it is a direct correlation. You can see how CD, the drag coefficient, is related to the Reynolds number. Okay. Okay, let's go to the next question. Select the correct equation for the linear velocity profile where u is the velocity, capital U is the local velocity, and delta is the displacement thickness. And the options are, this is also you can directly get from the lecture notes or the lecture content. You can directly get which of these will be the correct expression. So yes, the correct equation for the linear velocity profile is nothing but the first option. Okay, the option A is correct. Okay. Okay. Now let's see the next question. In the laminar boundary layer flow over a flat plate, the ratio of delta by x varies as where d is the boundary layer thickness and x is the distance from the leading edge in the direction of flow, and how it is related to the Reynolds number for a laminar boundary layer flow. So this is not D, this is delta. Okay, so this also you can get from the lecture slides, how delta by x is related to the Reynolds number. This is a direct relation. So if we have a laminar boundary layer, so how is this delta by x related to the Reynolds number? Like delta by x is equal to 5 by root over Reynolds number. So some kind of relation that is there, that is Rex, sorry. So this kind of relation, how it is related, that is delta by x, how it is related to the Reynolds number. So we know that the delta by x is proportional to Reynolds number to the power of -5. So these you can directly get from the lecture notes, from the lecture slides. So this theory, how it is coming, the boundary layer theory for this laminar flow. Okay. So from there you can get this relation directly. Okay. Okay. So now let's go to the next question.